Video is going to talk about Pythagorean trigonometric identities, and we're going to talk about identities. We're going to talk about where they come from and how to kind of use one identity to find more identities. And then the main idea is how can we use those ideas, the identities we already know, again, to prove, yep, I said the word, prove that other identities are true. So first of all, we usually can do really big proofs like the one over here at the left. Now, these are a little bit more technical, a little bit more, involved going on here. But again, not terribly difficult if we really think about it. I've got a triangle over here at the left, and what I'm trying to do is prove this identity at the bottom, sine squared plus cosine squared equals 1. Well, very simply, if I look at my triangle and x is my angle, then the cosine of x is b over c. The sine of x would be a over c. Now, I know the Pythagorean theorem is true, but really, if I think about it, if I take that Pythagorean theorem and I divide by c squared, right? Well, c squared on the right here divided by c squared would be 1. B squared over c squared and a squared over c squared, well, they're both squared terms. So if you remember some basic algebra, if we have a fraction that's squared, we can put that square onto both parts. Or what we're going to do, we're going to actually remove the square. If they're both squared, then I can call this a divided by c squared and b divided by c squared. The whole fraction is squared. And in that case, well, now let's go back to where we started. Remember that b over c was equal to the cosine, and a over c was equal to the sine. So therefore, what we just proved is if the Pythagorean theorem is true, right, the two legs of a triangle squared equals the hypotenuse squared, then the sine squared of x plus the cosine squared of x, right, sine of x quantity squared, cosine squared, would be equal to 1 as well. Now again, that's a very elaborate proof to find an identity. The beauty is once we know some identities, like sine squared plus cosine squared equals 1, very helpful identity, we can prove more identities. And we can do that in a fairly simple fashion much of the time. If I take a look at this identity here, what if I divided all of the terms, right, both sides of my equation, perfectly legal, by sine squared? Well, you'll notice sine squared divided by sine squared, cosine squared divided by sine squared, and 1 over sine squared. Well, sine squared over sine squared should be equal to 1. Cosine over the sine is really the same thing as the cotangent. We know that from the quotient formulas. And 1 over the sine is really cosecant. So 1 over sine squared is really just cosecant times cosecant, or basically cosecant squared. And we've just proven another Pythagorean identity. Let's do the same thing. Let's take the original. Let's divide by cosine squared. Sine over cosine is normally we say is equal to the tangent. Cosine divided by itself would come out to 1. And 1 over the cosine squared is secant squared, right? 1 over the cosine is secant. So if you have two of them, right, multiplied, it's really just 2 of them multiplied, secant squared. So again, there are 3 Pythagorean identities, 2 of which are basically just jump right off the other one. Right? We can do a fairly quick, easy set of algebra there and kind of prove more of them. Now, most of the time, when we try to prove identities, right, verify that identities are true, as the directions say, we try to stick to one side of the equation. We try not to mess with both sides at the same time. Because a lot of times when we're solving equations, we end up with extraneous solutions, because sometimes we take slight shortcuts. We kind of ignore some of the rules of math just because they generally they hold true. So a safer bet, rather than crossing that equal sign, we're going to be super careful. Our job is going to be to simplify or change one side of our equation to become the other side. Now, we can use some of our old identities to do so, though. Notice on the left side of the equation, over here on the left, I've got a cosine squared. Well, again, those Pythagorean identities, remember, they've got squared trig functions all over the place. So if I'm looking at a cosine squared, I'm thinking of this original Pythagorean identity, and I know that 1 is equal to sine squared plus cosine squared. So really, if I go back here, let's keep the original, right? And I'll make sure I write that one in black for you. Let's go ahead and keep the original. So we've got cosine squared of x on the top, and we've got a cosine of x on the bottom. We're also going to subtract, but instead of 1, I'm going to go ahead and remove that 1, and I'm going to call it sine squared, oops, not theta though, of x plus cosine squared of x. If we just do a little bit of arithmetic, we take that negative and distribute it to both parts, right? That's just basic algebra. cosine squared of x minus the sine squared of x plus the cosine squared of x. Right? Oops, not plus though. Again, I've got to distribute that negative. I worked so hard using those parentheses. Don't forget them. So again, we've got sine squared of x, distribute that negative, minus cosine squared of x all over the cosine of x. Well, a little basic algebra again, cosine squared minus cosine squared. We're left with a negative sine squared of x. Now I'm going to go ahead and write that as two separate things just because I'm thinking ahead a little bit. But again, that's what we're left with on top over the cosine of x. And then finally, notice what our goal was up here, right? We want a negative tangent of x sine of x. Well, hey, I've got that sine of x up top here, right? And remember our quotient properties, sine over cosine, right? Sine of x over cosine of x is really the tangent. So we can keep the negative. Again, this sine of x cosine of x right here becomes the tangent of x, and it's still multiplied by the other sine of x off to the side here, right? It's still multiplied over there. Well, since that was what I wanted to prove, I'm going to use a little bit of Latin. It's called quid ergo demonstratum. I'm going to say, therefore, QED. I demonstrated what I wanted to demonstrate. Now, you could rewrite this negative tan of x, sine of x, you could say equal to that right here, and equal to that right here, and equal to that right there. And you could rewrite that over and over and over. And that's not a bad way to do a proof either. But again, if I work one side, make it into the other side, right, and then say that I proved what I wanted to prove, that's a great way to go as well. Let's do that again on the right. Notice our goal is going to be equal to 1. So my goal is, let's try to make that left side, that big messy side, equal to 1. Now, I notice a set of parentheses there, and if you see that whole plus and minus thing, I'm very tempted right now to go ahead and distribute. So that's what I'm going to do. Secant times secant will be secant squared of x. On the outside, I've got the secant of x times a negative tangent of x. So secant x, tangent x. Inside, again, I've got tangent and secant. So again, positive secant x, tangent x. And then finally, tangent times negative tangent would be minus the tangent squared of x. Well, again, some basic algebra. We've got negative secant tangent plus secant tangent. Those are gone. So I'm going to go ahead and write out my steps. Now, one of the keys to proof is not to leave anyone behind. We don't want to take too many steps at once. So I'm trying to do one thing at a time here. So even though, yeah, I may be very familiar with, or I might have seen ahead of time that those terms would cancel, I still need to write that out. Again, we're showing a proof. You don't want to leave any steps out of a proof. It's like writing a novel and leaving a chapter out in the middle. You can't leave out the important parts of the story, right? So again, we're going to show that work. We're going to eliminate. We're going to get down to here. And now, wait a minute, I see those squares again. Let's go back to our Pythagoreans. Tangent squared of x plus 1 equals secant squared of x. So why don't we take out that secant squared, and we're going to replace it with, oops. So I'm going to take out that secant squared. I'm going to replace it with the tangent squared of x plus 1, and again, minus the tangent squared of x. Well, again, tangent squared minus tangent squared, and we're only left with 1, right? We've got that final answer. So again, rather than having to write out the fact that, oh, hey, and by the way, 1 was my goal, therefore, QED, I demonstrated what I wanted to demonstrate, right? Quid ergo demonstratum. We demonstrated what we wanted to demonstrate. If you have any questions about proving identities, make sure you talk to your teacher. Otherwise, have a great day.